stations there. I mean, we could make it like this if you wanted to, but we don't have to. But essentially, you know what the diffuser looks like. It looks like your sweet air problem that you've done for inlets. But essentially, let's assume that this is the diffuser. These are my stations that I have. One is the inlet of the engine. 2 is downstream of the diffuser. Between 2 and 3, that's where I have my fuel injection and my flame holding. 3 to 4 is really my heat addition through combustion. That's where I'm actually doing the combustion side of things. Then 4 to 5 is the choking point, and then 5 to 6 is your supersonic gas expansion that you can have. So we outlined a few assumptions that we're working on. We assumed initially that this is an ideal ramjet. We're going to also go over the equations for 9 ideal situations. It's actually straightforward if you all understand the ideal situation. So we drew our ideal temperature versus entropy diagram, and we said, okay, starting from ambient conditions right here, if I go through my diffuser, essentially I'm going to get thermal heating, and from there, but it's still isentropic, so ds is equal to 0, so I go to station 2 and 3. 2 and 3 are somewhat nominal. There's differences, but for an ideal ramjet, we don't consider drag. We don't consider any issues associated with, we assume homogeneous fuel distribution that's happening in there, which is not really the case. So we're assuming that 2 and 3 are, in this situation, are similar. And then from 3 to 4, that's your heat addition. So this is where your combustion is happening. And then from 4 to 5, which is your throw condition, is expansion, isotropic expansion, and then further isotropic expansion to the ambient conditions. That means it's ideally expanded because P6 is equal to P ambient at the exit, so you don't have to deal with the shock situation that you're dealing with in the project. So we outlined some independent parameters. We said, okay, we have our flight Mach number. That's determined by the requirement and the mission of the aircraft that you're working with. So that's sort of fixed. You're controlling it if you're designing the aircraft, but if Lockheed is telling you this is what we need, or the Pentagon is telling you this is what we need, this is what you need, you're stuck with it. Tmax, you control by that through your materials and your thermal cooling throughout the whole engine. Most likely your combustion temperatures are way, way hotter than the materials that you're ever going to use, and that's the challenge that we have today. We generate more efficient engines in combustion-based engines. The problem has always been Tmax. You're limited to how much really temperature you can have in there. And you're limited also by the type of fuel you're going to use and the equivalence ratio that you're going to be using. That also limits your conditions there. And type of fuels, your heat of combustion, which is your heat of input, and your ambient conditions. You don't control altitude conditions in general. You know what the atmospheric layer is like, you know your pressures and temperatures throughout. So these are inputs that are going into your engine that you have certain range of control, but these are inputs that are well defined. Now, dependent parameters, as a propulsion engineer, this is actually what you tweak around. You have your specific thrust, that's what you target as part of your engine. And your propulsive efficiency, your overload efficiency, your thermal efficiency, TSFC, these are control parameters that you actually design or develop your propulsion system based on. And the equations that are based on what we wrote before, specific thrust, propulsive efficiency, thermal efficiency, overall efficiency, and your TSFC. We're going to be using it, but I just want to outline it here. I'm just recapping what we went over last time. And building on that, we need to find some of these values. So how do I go and determine the values so I can substitute them in here? Because that's the end goal. But I need to primarily march through the engine. Like you're doing through that project, you're going to march through the whole engine and determine all the properties, temperatures, pressures, Mach numbers, and so forth. And that's what we're going to do. So we need to find these values. So, what are the values that we need to find? Well, the first thing I need to know is I have a flight Mach number as an input for the aircraft. I need to know my velocity is coming into my engine. So, because the flight Mach number is not helpful for me, so I need to know velocity, which we already know by definition. It's equal to the Mach number multiplied by gamma RT, or the speed of sound. Now, T here is the ambient temperature plus 2 of the atmospheric layer. So wherever you're at altitude, that temperature keeps changing. So the velocity will change and slightly down. Mach number will change depending on your flight envelope. So the way you can think of it is, in military engines, we treat it this way. These are their plots for routine. We say this is flight Mach number. And this is altitude. And depending on where you're at, this is ground level, sea level static, right here. You're not flying, the flight Mach number is 0. And sea level RAM is when you're right here, you're at the same level as the sea level, ground level, but you're ramming at really high Mach number. That's when you're going to air shows and your aircrafts are very close to you. That's that condition. And then up and away is this way. High speed RAM. We'll go over different conditions as we go through it. But this is the flight Mach number, meaning I control the speed of the aircraft and I control altitude. So that changes my propulsion system through this. So what do I need? Let's list our. Okay. I want to know the unknowns. So what do I have? I have the Mach number, flight Mach number, so I can get my velocity here based on this. It's an unknown factor. We'll do an example problem. The other one is I need to know my exit velocity, because right here, if I'm trying to get specific thrust, I need my exit velocity. Exit velocity is equal to m exit square root of gamma r t exit. Now, T at the exit is the static temperature within the engine. So I need to know my stagnation temperature. I need to know Mach number at that condition to actually compute my exit temperature from the engine. So we need M exit and T exit. Now, depending on the situation, you might be designing it as an ideally expanded situation where your exit pressures are equal, or like the project, but it's not ideally expanded and you have a shock there. And there is a reason why you're designing it based on a shock there, because we are going to add heat addition, and that's going to push that shock away. And when you try it with and without ideally expanded versus with the shock there, you will notice that the stagnation pressure is drastically higher. So, and that's what you're getting by just combustion, doing that combustion process there. So, anyway, assume ideally expanded. This is an ideal ramjet. P exit is equal to P ambient, and it's equal to P6. So remember your stations. These are fixed stations, by the way, but P6, your exit there. So if these are equal, then I could use my isentropic relations. P stagnation over P6 is equal to 1 plus gamma minus 1 over 2, Mach number at the exit squared, gamma over gamma minus 1. And same thing with temperatures, P stagnation 6 over T6 is equal to 1 plus gamma minus 1 over 2 and exit squared. So it's my isentropic relations that I'm used to. But from this, we need to find, we need T stagnation 6, we need T stagnation, well, T stagnation 6 is based on ambient, so I will know this. I need M exit, and So, if I know this, and I know my stagnation pressure, I can figure out my Mach number. Knowing my Mach number, I can come here and figure out my temperature ratios, which is again something that we're going to need to get the velocity, because I'm after this, or specific most, but to get this, I need my static temperature as well. So, we need to determine P stagnation 6, P stagnation 6, by walking through the engine. So, if I'm trying to determine the performance of this engine, meaning efficiency, thrust, ESFC, if I know the conditions at the exit of the engine, I don't need to bother computing all the stuff inside the engine, because I can use this information and couple it in with what we already drove as your dependent parameters, which are specific thrust, propulsive efficiency, overall efficiency, and thermal efficiency. However, you need the exit velocity. And if it's given to you, yeah, then just plug it junk and you got your values. However, that's not the case. You're always designing that engine. So you're controlling UE exit. So to control this, that means you have to determine all these different parameters. To determine these parameters, that means you have to go back again to that engine. Start from the inlet, right here. You know the air conditions are coming in. You pass it through the diffuser. You add the tools that you control. You burn. You have heat addition. And then you have a seating nozzle that you're expanding across. And then you're determining everything at the exit to eventually find out that last parameter you exit to plug it in here. Make sense? We'll do an example problem. So, anyway, so we need to walk through the engine. So let's dissect each component of the engine and walk through our equations before we do an example problem. All right, so we have the first thing is inlet and diffuser. And that's the same procedure that we want to do for all the different propulsion systems. We want to start walking through each propulsion system in the same fashion. So even when we get to turbojets, we'll do compressors first and all that. So that essentially, this is from station A to 2. Let's start putting this thing here somehow. So this right here, I want to walk from ambient condition all the way to 2. That's what I'm walking through. Okay, so what do I have? Well, since this is isentropic, I'm assuming my ideal situation. Therefore, my P stagnation at ambient is equal to my P stagnation at 2. Well, I'm assuming completely isentropic ideal situation, no losses from here to here. Make sense? So these are my stagnation properties. So if I know my stagnation properties, I could go and find my ambient condition for my stagnation pressure based on ambient condition is equal to 1 plus n minus 1 over 2. The flight Mach number squared, the power of over gamma minus 1. So I know this because, well, I don't control the atmosphere. So I don't control the atmosphere, so I have my static pressure coming in, and I control, well, primarily what Mach number of the aircraft is like. So I can substitute in here and find out my stagnation pressure. The stagnation pressure is really equal to stagnation pressure 2. So one thing to know is I don't have any work being done, and I don't have any heat being generated throughout the diffuser. It's not situations where we're applying suction and so forth and blowing inside the inlet, so that changes things. So anyway, we're gonna take it at 0, and then from that, once I know this, I could go and say, well, it's still ideally isotropic situation there, so it's P stagnation, T stagnation 2 is equal to T stagnation at the free stream, and therefore I can use my, if I know my temperature from the ambient, then I can say T stagnation A over TA is equal to 1 plus minus 1 over 2 and A squared. So nothing special there because I assume isotropic situation, so that makes it easy. Now, going through the combustion process, and that's where it gets a little bit challenging. That's where we spend quite a bit in reaction mixtures and so forth, because this is where we have a lot of terms to deal with. I mean, we simplify it to a simple equation, but it's important that we understand where the source of that comes from. So, let's apply the energy equation to the combustor. And just to recap, I'm going to split it the same fashion like we did in the past. We started first by getting the heat of combustion, and then we used that to determine the adiabatic flame temperature. Now, why is the adiabatic flame temperature very critical for us? Because it is Tmax that you have in the engine, and Tmax controls everything, the thrust, everything that you have. So, this is why you have to sort of first start with the heat of combustion, define the heat of combustion equation, then drive the energy for the gas expansion. The same exact process, if you remember right here. I'm going to walk through the equation, but I don't want you to be lost. Right here. This. We went in first, got the heat of combustion, and we said, oh, I got heat generated, but that heat is in an adiabatic process, assuming ideal situation, meaning that I have no heat loss across the combustor. And I'm going to route it back into the gas and heat up that gas and expand that gas. That's how the combustion process is actually happening. We want to accelerate the gas. Remember the boat problem, right, with the rocks. We want to move mass quicker inside, and the only way to do it is through that thermal heat addition process. So let's first do the heat of combustion and use that to define our adiabatic flame temperature. So what do I have? I have MA, same based on our conservation equations. I have some device of some sort, I'm adding some M fuel to it, and I'm getting heat output. Same exact process that we just said. But in reality, my combustor is nominally adiabatic. Therefore, the heat output is going to come back and heat up that gas that is generated due to the combustion process or the reaction process that you're having there. So that's equal to M product, which is equal to MA plus MF, conservation of mass. What comes in is equal to what goes out. So MF is equal to my fuel-air ratio multiplied by M dot A. Okay, well, fuel-air ratio is the mass of the fuel divided by the mass of the air they have in there. So, but this is a critical parameter because we use it quite a bit to control the engine. And I mentioned last time, this is the most parameter that you have in the engine that you control. It's always that power lever that the pilot uses. We call it PLA. It's this. It's really this. That's all you control. There is nothing schooling or anything. It's just how much fuel you're dumping into the engine. It's just your accelerator in your car. That's how you're controlling your car. So you're controlling primarily how much fuel you're putting into your combustion chamber. Okay, so if we do our energy balance there, well, I don't have any work there, so 0 is equal to minus out, because it's emanating out, plus M dot A multiplied by my enthalpy, plus M dot F multiplied by my enthalpy, minus plus here. The mass of products multiplied by its enthalpy. Well, let's define the enthalpies again. Well, I have enthalpy of A, that's most likely of air, in